Welcome back everyone to Flight Vehicle Dynamics. This is lecture 26 in week number 10. So today it's going to be mostly focused on the simulations on MATLAB of the perturbed system. But before that, I want to add one more thing. Since the reference trajectory that we're considering is at constant altitude, it is very convenient to introduce an equation of motion that describes the evolution of the perturbation in terms of altitude. In other words, we want to find a dh dot equation. And then we're going to add it to our equations. This is going to be a dependent equation, so it's not going to be another completely independent state. In fact, you can see that we can write the altitude as usual using the position, the coordinates in the body reference frame, xb, yb, and zb, and the Euler angles. So of course this function is contains some states. And if we take the time derivative of the altitude, well, we have a bunch of terms over here. We can manipulate them, insert the ODEs right here. I have another one and another one, right? And so after some manipulation, I'm not going to show it here because it's just, I'm not really interested in showing that. But anyway, you can get the rate of change of the altitude in terms of just some states. So we have the airspeed, V infinity, we have the side slip angle, beta, the angle of attack, alpha, and 2 out of 3 Euler angles. We have the pitch angle, theta, and the roll angle, phi. Now, of course, if we want to find delta H dot, so the perturbation, what we need to do is to linearize. So we take delta H dot is Jacobian, delta H over delta X evaluated at our reference trajectory times delta X plus delta H dot of partial U. We use the control vector, always evaluated at our reference trajectory, times the perturbed control vector delta U. You see that H dot is only a scalar, so delta H over delta X is really a scalar, a gradient vector, and so is delta H over delta U. So we can find that given the order that we used last time. So we're using X as XB, YB, ZB. And then we have the Euler angles, psi, theta, phi. And then we have V infinity, alpha, beta. And then finally, the components of the angular velocity, pu, q, and r. So if we use the state vector in this order, delta H dot is going to be a bunch of zeros, and the only non-zero components are the ones corresponding to the fifth element. So 1, 2, 3, 4, 5, 5, the pitch angle, and the eighth component, which is going to be the angle of attack. Then this other gradient is simply 0 because H does not contain any control. So of course, the derivative with respect to the control vector is going to be 0. So in the end, we're going to have that delta H dot. So the rate of change of the perturbation in the altitude is equal to V infinity trimmed times delta theta minus V infinity trimmed times delta A. Or more compact, V infinity trimmed, times delta theta minus delta alpha. Okay, so this is the ODE describing the rate of change of the perturbation of the altitude, but we need, of course, an initial condition, delta H0 at time 0. So recall the function that we used over here of H So we can say H is a function of XB, YB, and ZB. So delta H is partial H with respect to XB times delta XB plus delta H over delta YB and so on and so forth. And these partial derivatives have to be computed at the reference points. In this case, we have the angles, and the reference values are for the pitch angle is equal to the angle of attack, so alpha star, and the trim value for the roll angle is simply 0. So we have that the initial condition, delta H0, is simply sine of alpha star times delta XB naught minus cosine of alpha star times delta ZB naught. So delta XB naught and delta ZB naught are the initial perturbations in the X direction and in the Z direction, if we have any. And overall, delta H naught is the initial perturbation in terms of altitude. All right, so let's jump to the Mathematica file. Let's take a look again at the perturbed equation. And I want you to notice something very interesting. All right, so what I did here, well, I added this DH equation that we found. Well, here we don't really need to fully simplify. Okay, so I've added this equation that we just got for delta H. Well, actually, this is H dot. So in order to find delta H dot, we have to linearize the whole system. But anyway, I rearranged the states in a particular manner. I already know the answer, so that's why I chose this particular configuration of the state, or a particular order of the state. But anyhow, just try to follow me here. I chose the first two positions, X and Z, so everything that happens in the longitudinal plane of symmetry of the airplane, the pitch angle, which is the angle of rotation about the Y body axis, then the airspeed, the infinity, the angle of attack, alpha, the Q, the second component of the angular velocity, and these are the first 6. And then the second 6 are the side slip angle, the Y component, then yaw, roll angle, and the other two components of the angular velocity, P and R. And then when it comes to the control vector, I put first the elevator deflection, then the thrust, and then the deflections for the aileron and the rudder. So now let's do exactly what we did last time with the addition of our dH, the partial derivative, in order to find what I just found in the notes. But here, keep in mind that since the order of the states is a little bit modified, this V infinity star or V infinity 0 here in Mathematica, n minus b infinity 0 is they're gonna be at different positions. Let's check if indeed they're correct. So we have v infinity 0 is the third position and corresponds to theta, which is what we found earlier, and this minus v infinity 0 is the fifth position, which corresponds to alpha. So that's exactly what we found in the notes. Now, what we do, of course, we find the Jacobian A, so vector field F. We take the matrix of all the first derivatives with respect to the state, and we find the Jacobian. That's exactly what I described last time. But now take a look with this different order of states, we can see something very peculiar happening at the for this matrix. You see that, now I'm going to scroll laterally so maybe you can notice that this matrix is diagonal in blocks. And what I mean is that we have a whole block over here with, it's a 6 by 6 submatrix, which is sort of a full matrix. And then we have a whole matrix of 0 in the non-diagonal block. And then when we go to the second part of the matrix, we have the non-diagonal block. The upper block is still a 6 by 6 matrix full of zeros, and the lower diagonal block, 6 by 6 one as well, has mostly non-zero terms. So this means that we have states that are decoupled from other states. And in fact, we have the first 6 states, x, z, theta, v infinity, alpha, and q, whose linearized dynamics are decoupled from the other states, the side-slip angle, the y component, the yaw and the roll angle, and p and r. Well, that's great. It's going to simplify greatly our analysis. And in fact, the first 6 states represent the so-called longitudinal dynamics of the airplane, whereas the other 6 represent the lateral dynamics of the airplane. Similarly, this can be seen also when we take the Jacobian of, so the derivative of the vector field with respect to the control vector u. So remember, we have this tall matrix, but now if we order it so that we have the elevator, the thrust, the aileron, and the rudder, we still have this submatrix here and submatrix over here full of zeros. So it means that we can also decouple the effect of the control. So in other words, the elevator and the thrust are only gonna influence the longitudinal dynamics, so the motion in the xz plane, whereas the rudder and the aileron will, the commands in the aileron and in the rudder will influence the lateral dynamics of the airplane. Okay, these last 3 lines is just the derivative of h dot with respect to the control vector u, and it's just 0, 0, 0 as predicted. So now let's go back to the notes, and then we're going to see in MATLAB if indeed we can find a decoupling of the 2 dynamics. All right, so as I said, we found 2 groups of states that can be separated because the dynamics, the linearized dynamics at least, involving these 6 states is different and decoupled from the dynamics described by these other 6 states. As a matter of fact, it should be all delta because here we're dealing with actually the perturbation. It's a linearized system. Sometimes in books, you're not going to find this little delta here because they just drop it for sake of, saving some ink. But anyway, always remember here that we're dealing with the perturbed dynamics. All right, so we can actually separate the systems into the big system into 2 systems. And usually in the longitudinal dynamics, the x and y and z dot equations are replaced by the delta H dot equation. So we're not going to find delta xb dot and delta zb dot. And the reason is that here we're considering things, the reference trajectory is a trimmed level cruise flight. And all we really imposed is the fact that the plane has to go at a constant airspeed at a constant altitude. So we haven't really specified anything when it comes to the trajectory of the airplane. So we don't really care if these 2 terms or the perturbation in terms of the xb, zb, or indeed in the yb coordinate go to 0 or not. We really care about the other states and the altitude. So that's why we included the altitude in the longitudinal dynamics. While the altitude in the longitudinal dynamics, because obviously the altitude isn't just in the z direction in the inertial reference frame, which is a combination of the x and the z body reference frame axes. All right, so when it comes to the lateral dynamics, we consider these other 5 states. So once again, we don't really care about yb dot for the reason that I just told you. So we are left really with 5 equations: the side slip angle, yaw angle, roll angle, and P and R. And so we have these 4 sub-matrices here, this A longitudinal and A lateral, that are both 5 by 5 matrices, and the B longitudinal and B lateral are both 5 by 2. You see, as we said, we can also decouple the effect of the controls. So the elevator and the thrust will influence only the longitudinal motion of the airplane, whereas the aileron and the rudder input will only influence the lateral dynamics of the airplane. All right, so let's take a look at what happens when we go and simulate. All right, so here we have our code, always referring to the Boeing 747-100. So these data here are the same that we've used for homework number 5. And then here we have a bunch of coefficients and the sensitivities for the drag, the lift, the pitching moment coefficient, the side force, the yawing moment, and the rolling moment coefficients. So we have a bunch of them. And we have the cruise conditions. We still are keeping that Mach 0.8 and an altitude of 40,000 feet. Well, here it should be really trimmed altitude. And we have the atmospheric model constants, and we conversions. And then here we list all the trim values that we're using and that we found in the last lecture. So we have the trimmed air density, the trimmed air temperature, the trimmed speed of sound. Then we can calculate the trimmed air speed by multiplying the Mach number by the speed of sound, the dynamic pressure, and the epsilon, which is simply the weight of the aircraft, m times g divided by the dynamic pressure times the wing surface area. As usual, we find our trimmed angle of attack by first solving a linear system and then using the solution of the linear system as the initial condition for our FSOL function that solves the nonlinear equation in the angle of attack alpha. So we find alpha 0, or our trimmed value for alpha. Now we have to specify the initial conditions in terms of perturbations, because now we are going to simulate the perturbed flight. So we have to specify all the perturbations in all our states and controls. So for now, I'm going to put everything equals 0. Then we have this parameters vector that we're going to feed into our ODE function. Initial and final time as usual, initial state and control perturbation vectors. So we have the states over here. We have 12 of them plus the altitude, because I'm going to integrate also the altitude perturbation as well. And then we have the 4 controls. Here I didn't modify the order of the states like I did in the mathematical file. I kept the older order that we saw in the previous lecture. Again, in the simulation is not a big deal if you change the order, as long as you are consistent when you write the equations in the ODE function. Okay, so then we call the ODE45 and then we elaborate the results plotting a bunch of things. So let's go and take a look at the function containing the equations of motion. So, well, we have all the parameters here. A couple of them, well, three of them, we're not really going to use them, but I still call them no matter what, just in case they are non-zero for other examples. Now, in this function, I'm simply going to use alpha, q, v, h, de, cd, cl for, even though all these values over here refer to the trim condition. So these are trim conditions that I'm going to feed into our A and B matrices. So here, nothing really fancy, it's just the A matrix that we found in Mathematica and the B matrix. So these are all, these matrices contain all the first order partial derivatives of the vector field with respect to the state and the vector. So here, although I'm including the altitude in the state Y, but the matrix A is still a 12 by 12, so I'm going to have the first 12 ordinary differential equations as we would expect for our perturbed system, AX plus BU, and then the last one involving only the perturbation in terms of the altitude only has, it's only a scalar equation, because, well, this is a vector, a row vector, but X is a column vector of the same size. So this is a 1 by 12 times a 12 by 1 is going to be a 1 by 1, so a scalar. All right, so let's see what we are getting. And let's first try the case with all the perturbations are 0. All right, so I guess the figure that is more interesting here to look at is figure number 1. So I divided into parts the longitudinal dynamics and the lateral dynamics. So the 5 plots to the left contain all the states that define the longitudinal dynamics, whereas the 5 states on the right represent lateral dynamics. Now everything is 0 because the initial condition is 0. Nothing is not really interesting in this case. So let's start by giving an initial perturbation of some kind. So let's give it a little bit more airspeed. Let's say we increase the airspeed. We have a sudden change of 10 meters per second. Let's see what happens. So V infinity is one of the longitudinal states, so we expect only the longitudinal dynamics to be modified. Is that the case? Well, yes, it's indeed the case. So we had an initial perturbation of 10 meters per second when it comes to the airspeed. And then as the time goes by, this settles at a little perturbed. So it's not gonna go back to 0. So we're gonna have an increase in the airspeed and our trimmed airspeed. So the angle of attack starts by decreasing, then increases, oscillates, but it's damped, and I believe it will eventually go to 0. This is again delta alpha, so it will go to the trimmed value of the angle of attack. Remember, here we are visualizing the difference between the actual state and the trimmed state. So if the trimmed angle of attack was about 5 degrees, as we saw in the homework, well, it means that here it's going to go to about 4.4 and then 5.3, and then it will settle and eventually go to the trim condition of about 5 degrees. Let's see what happens with the altitude. We have an increase in altitude, and then we lose a little bit of altitude, and then we're gonna stabilize at about 175 meters above the altitude of reference. So this initial perturbation in terms of airspeed will cause us to gain a little bit of altitude and remain at this new altitude. So if we wanted to go back to our original altitude, we would have to perform some sort of maneuver. But anyway, this is just an example that shows you that the perturbation in V infinity in the airspeed only affects the longitudinal states as we predicted. So let's now perturb another longitudinal state, and let's see if that is maintained. So let's also give a little bit of perturbation in terms of angle of attack. So we increase the angle of attack by 3 degrees. And yes, as expected, only the states describing the longitudinal dynamics are affected. There's nothing that goes on in terms of lateral dynamics. So the aircraft just moves pretty much up and down and pitches, but it doesn't move from the XZ plane. The other two figures, this one contains the perturbations in the state, XB, YB, and ZB. And again, this is not really super interesting, but just see that XB and ZB were in the longitudinal states, and in fact, they are the two that are being affected, whereas YB is absolutely not affected by the initial perturbation in the airspeed and in the angle of attack. So now let's zero these and let's give an initial perturbation in terms of some states that describe or that influence the lateral dynamics. So let's give it an initial angular velocity delta p of 2 degrees per second. So the aircraft suddenly has acquired an initial pitching angular velocity of 2 degrees per second. Let's see what happens. Oh, you see that the lateral dynamics states have changed now. And it seems here the lateral dynamics is way more responsive. So we're getting to a steady state value much faster than when it comes to the longitudinal dynamics. So just in a matter of seconds, we've restored our side slip angle to 0, and also our perturbation in terms of roll angle has gone back to 0. The components of the angular velocity for the perturbations, delta p and delta r, went to 0. But we've acquired a constant yaw angle. So we've changed our direction of our plane. Now we're not going straight anymore. We've turned a little. Now we're still going straight, but we've turned from our initial trajectory, because now the yaw angle is, well, it's pretty small, but it's still non-zero. And of course, you can play with this, and I'm gonna publish. I'm gonna post this code on Carmen, so you can play with it and see what happens. Now let's take a look at the control. If we give a little perturbation in terms of control, so let's say the ailerons suddenly get stuck. So at let's say 5 degrees. Yeah, this is, sorry, radians, radians per second. Okay. So let's see what happens. All right, so once again, only the lateral dynamics have been affected. Here the aileron is stuck, so we're turning. See, we keep changing linearly the yaw angle, so it means that we're turning to the to the right. And then we're also kind of going sideways a little bit because the side slip angle is non-zero. And there's also a roll angle of about 1.1 degrees. And although the rolling velocity, or the p component of the angular velocity, has gone back to zero, the velocity, the angular velocity in the z direction, now is constant. So that's why we're turning, or we're changing linearly our yaw angle. All right, so I suggest you, well, just have fun with the code and see a few things. Of course, here, well, it's nice, everything is combined. So what we're going to do next time is to actually write down the lateral dynamics and the longitudinal dynamics separately. So we don't have to deal with this bigger system. And then we can analyze the stability. In this case, we already have all the coefficients here that have been, the plane have been designed so that it is stable, it reacts in a certain way. But what if you have to design the airplane? Well, you have to come up with these numbers over here. So dealing with all these coefficients, all these equations is not very easy when it comes to designing things. That's why already the fact that we can decouple the lateral dynamics with the longitudinal dynamics, well, it's a great help. But of course, keep in mind that these perturbation dynamics, so the linearized equations describing the change in time of the perturbations, well, they depend on your reference trajectory. And in this case, we have the level cruise trim condition, which is the easiest of them all. So if we had a coordinated turn, we would have to rebuild all our A matrix and B matrix for the new reference trajectory and reference. Well, of course, reference trajectory is always reference state plus reference control. All right, so this is all for today, and I'll see you virtually next time. In the meantime, take care.